Hello, everyone. We'll go ahead and start as people start trickling in. Welcome to lecture 2. Today I'm going to be one of your lecturers. My name is Ashley, and one of your other lecturers today is going to be Jennifer. She'll do the other half of the lecture. Today we're going to Nomenclature and Newman Projections. So this is a little overview about the topics we're going to be talking about today. We're going to start talking about alkane nomenclature, right? So let's start with that. So what are alkanes, right? So alkanes are just molecules that have single bond between carbons. So you see an example right there, where you can see this molecule, right? Oh, let me not draw. Right here, right? So each carbon only has a single bond to other carbons, right? So if you guys remember from Monday lecture, right, each end or each corner is a carbon, right? And then the hydrogens are implied that they're there. So this is a skeletal drawing. So again, alkanes are just single bonds between carbons, right? So this is different again from an alkene because alkenes have double bonds between carbons. So you can see that between this carbon and this carbon, there is a double bond. And then alkynes have a triple bond between carbons. So between this carbon and this carbon, there is a triple bond, okay? So today we're just gonna focus on alkanes and alkanes nomenclature. So nomenclature is how we name molecules in chemistry, right? So we're gonna start simple with just alkanes like this, which are unbranched, and I'll explain a little bit more on what unbranched means, but let's go ahead and start with that. So this chart looks like a lot, but these are terms you guys have to kind of familiarize yourself with naming molecules, right? So let's look at some of these. So right here, this is CH4, right? So 1 carbon and 4 hydrogens. That is called a methane, right? So these terms are kind of the foundation to starting to name more complex molecules. Right now, these are again alkanes, which are just single bonds between carbons, right? And then you have C2H6, which is an ethane. So 2 carbons and 6 hydrogens. You have propane, which is C3H8, which again 3 carbons and 8 hydrogens is a propane. And then butane with 4 hydrogens and 10 hydrogens and 4 carbons. And then you have pentane right here with 5 carbons and 12 hydrogens. And then hexane, 6 carbons and 14 hydrogens. And then heptane, 7 carbons and 16 hydrogens. Okay, so then octane sounds like 8, right? Sort of 8 carbons and then 18 hydrogens, right? So all of these again are just simple alkanes, right? Single bonds, and they're also just unbranched, meaning like let me draw the propane right here. Again, propane is C3H8, right? So we're just going to draw a simple 1, 2, 3 carbons, right? Butane is just going to be 1, 2, 3, so 4 carbons, right? Again, each peak, each end is a carbon, so this one's 4. They're unbranched, they're just a line. So a more simple way to learn this chart is to just memorize that methane has 1 carbon, ethane has 2 carbons, propane has 3 carbons, and so far down the line, and then memorizing this formula that I'm going to write right here. So CnH2n plus 2, right? So memorize the number of, so it's just showing up, but memorize the number of carbons, right? So again, methane is 1 carbon, ethane is 2 carbons, propane is 3 carbons, butane is 4, and then memorizing that H is 2n plus 2 hydrogens, right? So let's do an example for methane. So methane, again, we memorize that for carbons, n equals 1, right? 1 carbon for methane. And then we can just use the formula to calculate the hydrogens, just 2n plus 2, right? So, sorry, my handwriting is bad, I need to work on that. So again, the n was just 2, so just 2 times 1 plus 2. So this is just 4, right? So 4 hydrogens. So So you can just memorize that, methane is 1 carbon, and then just figure out using this formula the number of hydrogens. And then this is kind of the foundation to naming more complex molecules. So it is important that you guys kind of familiarize yourself with that. And I had mentioned that this is for unbranched alkanes. So as it says right here, unbranched alkanes. So what does that mean, right? So let's go to the next slide so it can be a little bit more clear. So unbranched alkanes, again, are like, this is an example right here, are just kind of like a straight line of carbon, like a straight chain of carbons, right? So unbranched alkanes are named based on the number of carbons. So in this case, again, kind of what we talked about on Monday, each peak and each end is a carbon, right? So we have 1 carbon, 2 carbon, 3 carbon, 4 carbons, and 5 carbons, right? So this unbranched alkane is named just based on the number of carbons, right? So we said that this was 1, 2, 3, 4, 5 carbons. We go to the last slide, and then we see again that pentane right here is 5 carbons, right? And we can figure out using this chart that this molecule right here is actually pentane. So just based on the number of carbons, we can name unbranched alkanes. When it comes to branched alkanes, right? So something like this. So by branched, I mean you can't just like follow it all the way through, right? There's like this line right here, this branch right here. So that's what I mean by branched alkanes, right? For this one, unfortunately, you can't just do the same thing as we did here, count the carbons, go to the chart, and then find, kind of match the number of carbons with the name. Unfortunately, there's more steps that you have to do instead of just counting the carbons. So I'm going to introduce you onto how to do that. Also, feel free to stop me if you have any questions. If I'm going too fast. If you have a question, you can also ask on the chat. Hopefully, Jennifer might be able to answer it. Okay, so how do we name branch alkanes? Okay, so an example of a branch alkane is right here, right? So at first, the first step is to determine the principal chain, right? So the principal chain, what that means is just the longest carbon chain, emphasis on carbon, right? We're just looking at the carbons. So here it's already in pink, but it's, it's already there. But in exams, they might not tell you this is the principal chain, so you have to figure that out, right? So how do you doing that, right? So to find the longest carbon chain, you kind of have to do trial and error. Here it might be a little obvious because of the way it's kind of drawn here, right? But let's just try it out, right? So it has to be a chain, right? So no branching, so you're looking at chains, right? So one of the possibilities can be this right here, right? It's just a chain you can follow it through. Right here, it's only 4 carbons, right? So that's one possibility, 4 carbons. Another possibility can be right here. And again, by chain, no branches, so just you can follow it through with a line like this. So this one right here has 1, 2, 3, 4, 5 carbons, okay? So this one's longer than the one we have previously looked at. So this one right here is the best choice as of right now. And then we have this possibility right here again, a chain you could just follow through with the line without having branches. So that right there is an option. This one has 1, 2, 3, 4, 5, 6 carbons, right? So again, the other one was 5, the other one was 4, this is 6. So this one's the longest carbon chain. So this is going to be the principal chain. Okay. So this one was a little bit straightforward and simple, right? That might not always be the case. It might be a little bit more complex, a little bit, take a little bit more thinking. So an example right here, you see 2 molecules right here. These 2 are the same molecules. They just have different carbons highlighted. So this right here is a 6 carbon chain, and this right here is a 6 carbon chain. Again, these are the same 2 molecules, right? But you have 2 possibilities for the principal chain, right? Since they're the same length, right? Either or can be the principal chain. So when you come into a situation like this where you have 2 or more chains that have the same length, how do you figure out which one is your principal chain, right? Because there can only be one principal chain, so we're just looking for which one would work best. So in this case, if we run into that problem, we have to look at which of these two possibilities have the greatest number of branches, right? And by branches, I mean anything that is attached to the principal chain that is actually like not the principal chain. So anything attached to the principal chain that's not the principal chain, right? So in this blue one right here, this is one of the possibilities of principal chain we're looking at. So this is a principal chain. What is attached to it is this right here, right? So that is a branch, right? It's not the principal chain, but it's attached to the principal chain. So this possibility right here has only one branch. If we look at this one right here, we can see that this is a principal chain in pink that we're thinking that it's a possibility, right? And then we see one chain right here, and then two chains right here. Sorry, branches. One branch right here, and then another branch right here. Okay, so we're gonna choose the one that has more branches. So in this case, this molecule right here, because it has 1 and 2 branches versus just this one branch, we're gonna go with this one. This is gonna be our best option. So if we run into this problem where we have 2 or more chains that have the same length, we look at which chain greatest number of branches attached to the principal chain. And again, branches are, yes, no, do you have a question?
Yeah, so for the structure on the right, if you made, so on the left end of the principal chain, if you changed the carbon on the left to be the carbon below it instead, yeah, like that, would that like be make any difference at all in terms of like naming or
Yeah,
anything?
so that's a great question. So in this case, it's kind of the same thing. So the difference between the one in pink and the one I circled, there's really no difference because the branching would be the same. So this, right, this is like where they start branching, right? If you switch it to the one you talked about, there's still one branching to the same carbon that is the same length at the same number of carbon. So there really is no difference. Hopefully that made sense.
Okay, yeah, thank you.
That was a good question. So yeah, hopefully this made sense. Okay, so then once you have determined the principal chain, which is the longest carbon chain, we can move on to numbering the chain itself. So there's two possibilities of where you can start numbering, right? You can start from, or you can start from this other side, this carbon right here, right? So you can see these are already numbered, right? So we're gonna focus on the blue one started from this carbon, 5, 6. And then if we focus on the pink one, again, 1, 2, 3, 4, 5, 6, right? So then in this case, right, what we're focusing on is which one of these numbering options, whether you start from your right end or the left end, are going to give this branch right here, this one right here, because again, this is our principal chain. So this is which of these numberings are going to give this branch the smallest number. So if we look at this blue one right here, right, the numbering on this carbon as to where this substituent is attached to is number 4, right? So if we start from this side, this is going to get a number 4. If we start from this side over here with the pink numbering, this numbering, this carbon where this substituent is attached to has a number 3. So we're going to want to choose the top numbering right here, where this carbon right here where this substituent has the carbon which is attached to number 3. Okay, so we're going to go with the lowest number as to which this substituent gets. So we're going to start with the pink one. Okay, so once we are able to number that and know where to number it from, and if this has more branches, it's, it can have several different branches. It's still the same process, just whichever one branches the lowest number. Okay. So next one was, once we have numbered the principal chain, right, based on which branching has the lowest number, we can start actually naming this. So right here. So we're going to start looking at the substituent. So substituent is another word we use for branching. So this right here is called a substituent. In this case, this may look familiar, right? We had talked about methane before. Methane with CH4. Sorry, my handwriting is horrible. Hopefully that makes sense. If it doesn't, feel free to ask me. So methane with CH4, right? So this substituent right here looks similar to CH4, but not exactly, right? So this substituent is derived from the alkane methane, right? But it's not methane, right? So these substituents that are derived from alkane, and they're called alkyl groups. And the way we figure out the name for alkyl groups is, since it's similar to methane, we're just going to replace the ane, again, ane for alkane, with YL, so YL. And if my handwriting is too ugly, it's right there, YL. So we're going to replace just ane with YL, so it's going to be methyl. So this substituent right here is going to be called a methyl. And there's some more examples here if you guys want to look at those. But in this case, it's just methyl. We had also figured out the principal chain based on which one gave the branch or the substituent the lowest number. So we know that this substituent is attached to the carbon 3. So this is called a 3-methyl substituent. Okay, so you guys notice 3-methyl has a hyphen right here. Hyphens are used to separate numbers and words. Okay, so whenever you have a hyphen in a word, make sure to whenever you have a number in a word, make sure to add the hyphen in between. So now we named the substituent 3 dash or hyphen methyl. Now we can name the rest of the principal chain. And this is going to be kind of like naming the unbranched alkanes, right? What we can do is just focus on the principal chain right here. Again, we number it 1, 2, 3, 4, 5, 6 carbons, right? So this is just hexane for 6 carbons. And it's okay if you guys haven't memorized that yet. You literally just looked at it, but this is a hexane, right? So what you're going to do is you're going to add the substituent name, so substituent name and number in front of the principal chain, which is hexane. So this is going to be a 3-methyl hexane. Okay. So we already finished naming this molecule, right? This was a pretty straightforward molecule. What if, I'm going to give you guys another scenario. So what if in the case, instead of having this methyl, we have Br, which is a bromine, right? So before we actually try to name that, I'm going to tell you guys that if you have substituents that are like chlorine, bromine, or fluorine, right? They're going to be named, so their substituents are going to be chloro, bromo, and fluoro. Hopefully I spell that correctly. There you go. So chloro, bromo, and fluoro, right? So let's try naming this molecule right here that I just replaced with this Br replaced with the CH3. It's going to be the same thing. We find the principal chain, number the chain based on which one gives the bromine the lowest numbering. So it's going to be the same way we numbered the other one because it's in the same place. So there you go, 1, 2, 3, 4, 5, 6. So then we kind of just start numbering, our substituent, which is in the carbon 3, and then 3 bromo, and then hexane. Okay, so it's still a substituent, so it goes in front of the principal chain, but now it's a bromo, and you do the same thing if you have a chlorine, so it's going to be 3-chlorohexane if it has a chlorine, or it could be fluoro 3-bromohexane. Okay, so I'm going to give you guys another example. So let's say we're going to replace this one again with bromine, and then replace this H right here again, also with bromine. So you have 2 bromine carbon, the carbon label number 3. right? So you have two things attached to the third carbon. How do you name this, right? So this is going to be 3, comma 3. So 3 because you have two bromines, two substituent bromines attached to the 3, right? And we separate numbers with commas. So you see the comma right there. Sorry for my handwriting again. So 3, comma 3, and then dash because we're going to add words with hyphens or dashes, whatever you want to call it. And then it's a bromo, right? But there's two bromos. So the way that we say that it's two bromos is by adding a di. So di for 2, dibromo hexane, because the parent chain is still the same. Okay, so in the case that there were, instead of just 2, so that is a D, by the way. So 2, so there's 2 bromos. If there was 3 bromos, we would say tribromo hexane. So it's 3, comma 3, again, separating numbers with commas, separating words with hyphens. So that's how you would name this. So I'm gonna give you a different scenario, but now with a ring, right? So this ring has 1, 2, 3, 4, 5, 6 carbons, right? So this, right, has 6 carbons. The way we dictate rings, right? So this is a ring, is by adding cyclo, and then adding, kind of using the chart, how many carbons this has.
Yeah.
6.
So
Yeah.
like my fate to get in somewhere, but I feel like we don't look enough alike. And I feel like it's gonna get taken somewhere.
Oh, sorry, Sydney, can you mute yourself? Thank you. Sorry, I thought you were asking me a question. But yeah, this is a cyclohexane. Is there any questions from anything I've done so far? Okay, so this is how we name branch alkanes and non-branch alkanes. This can become a little bit more when you bring out alkenes and alkynes, and then more branching, this can become a lot more complicated. So this takes a lot of practice. And there's a lot of information to take in. So at first, but practice will eventually, make this a little bit easier. So now we're done with nomenclature. I'm gonna ignore that slide. We're gonna talk a little bit about functional groups. So functional groups in organic chemistry are similar to what we've been talking about right now. So you can see your alkane right here, your alkene that we talked about briefly, your alkyne, right? Some of these other ones might seem familiar. You have your alcohol right here, right? That seems familiar. These are important in organic chemistry because they change, they're important for the reactivity of molecules. If a certain molecule has, for example, an alcohol, it can also, affect its boiling point, right? If it has a OH, it can have more hydrogen bonds, the boiling point of certain molecules. So these are important for reactions as well. Some of these are going to come later in the lectures, right? So for now, I just want to focus on talking about or briefly mentioning alpha halides, aldehydes, and ketones, as well as carboxylic acids. So let's start with aldehyde. Aldehyde, you can see that right here it says C. It has a C double bonded with O. So this is actually called a carbonyl group. So that's a carbonyl group. So aldehydes has a carbonyl group. The R again means rest of the molecule. And then this carbonyl carbon, right? Because this is a carbonyl group. The C is from that group, so it's called a carbonyl carbon, is attached to a hydrogen. So this is an aldehyde, a carbonyl group where the carbon of the carbonyl group is attached to an H, right there. And then a ketone has a carbonyl group, and then it's usually in between chains, because as you can see here, there's rest of the molecule here, rest of the molecule here. So usually it's somewhere in between molecules. You have the carboxylic acid, which has a carbonyl group right here, where the carbonyl carbon is attached to an OH. Okay, these are going to become important later on. So right now they might seem unfamiliar, but just familiarize yourself with these molecules as they'll become important later. And you have an alkyl halide, sorry, halo alkane right here, and where the R is the rest of the group, and X can be any of these right here, fluorine, chlorine, or bromine. So these are going to come again in later lectures when we talk about them reacting and reactions. So that is me for now. I'm going to switch it over to Jennifer.
All right, thanks so much, Ashley. All right. So I'm going to be talking to you guys today about Newman projections. Okay. All right, so back on topic. So Newman projections, they're essentially another way that we can draw organic molecules. It's going to be super useful in this course. Let me full screen this actually. Oops. Okay, so we've actually learned a couple of ways to draw molecules in the past in general chemistry. So I'm just going to run through that very quickly. So let's look at a molecule that Ashley was just talking about, so methane. So that suffix ane, what kind of molecule is this? Is this going to be an alkane, an alkene, an alkylide, an alcohol? What kind of molecule is this? And feel free to just chime up or chime in.
Alkane.
Exactly, it's an alkane. So it's going to have carbon-carbon single. Remember how many carbons are in this molecule?
Just one.
Exactly. I know that Ashley gave you a really useful formula for figuring how many hydrogens are in a molecule or in an alkane, and also you can just memorize it. But also when you're drawing it, it's also very easy to see how many carbons there are or how many hydrogens there are just from understanding how molecules work. So there's going to be one carbon. And how many bonds does carbon want to make in order to form a full octet? Does anyone remember?
4.
Yeah, exactly, 4. So in hydrocarbons, carbon is just bonding the hydrogen. So it's going to form 4 bonds to 4 hydrogens. So if you're going to draw the 2D structure, or like the skeletal structure, it would look something like this. So just carbon, 4 hydrogens. So now let's draw the 3D structure. You guys might remember the line wedge conventions from Gen Chem. And so does anyone remember what kind of shape this is going to be? It's a carbon that's a central atom and it's bonded to 4 different groups.
Tetrahedron.
Exactly, a tetrahedral. And then the simplest way to draw a tetrahedral would be something like this, where you have 2 bonds that are in the plane of the board, and then one that's sticking out and one that's going in. So you essentially have like a pyramid and then one bond sticking up. Okay, so now let's draw a slightly bigger molecule. So ethane, does anyone remember how many carbons are here?
2.
Exactly, 2 carbons. And then we can just fill in the hydrogens. So we know that carbon's going to want to form 4 bonds. And each carbon is already bonded to 1 carbon. So it just needs 3 more hydrogen bonds, something like this. And so now let's try drawing the 3D geometry. So each carbon, it's still going to want to be a tetrahedral. But now you have to draw 2 tetrahedrals right next to each other. So the easiest way to do that is to always keep your carbon-carbon bonds within the plane of the board. Usually your carbon-carbon bonds are going to be like the backbone if you're drawing. And then you would make your substituents the wedges and the dashes. So you draw something like this, where you would have your pyramid of hydrogen sticking out here, and then a pyramid of hydrogen sticking out here. And notice the way I've drawn this particular one. So in this one, I've chosen to draw these hydrogens up here in yellow. They're in the same plane. These hydrogens here in blue, they're both going into the page. And these hydrogens here in red, they're sticking out of the page. And let's actually look at what this is going to look like. So I've included this link in the PowerPoint, but oh God, I forgot I can't view anything when I'm doing this. Oh God. 1 second. I might have to just reload it. Okay, this works. Just load. This is the molecule that I've just drawn, this ethane. So these gray circles, these are the carbons. These white circles, those are the hydrogens. And as you can see, it's literally as I've drawn it. So these, why does it keep reloading? Okay. Eventually it'll stop rotating. But anyway, yeah, these hydrogens, they're in the same plane. these hydrogens are kind of in the same plane, and these hydrogens same plane. Wow, okay. And what does that mean? So essentially, if you were to view it from the side, okay, hold on, give me a second here. Okay, sorry about that. Okay, so let's look at this molecule. So it's literally as I've drawn it. So from what I've drawn, you have these hydrogens are sticking out, these hydrogens are coming out, these hydrogens are coming in, and I'm actually gonna make this a new tab. I'm just gonna have to switch back and forth like this really quickly. I forgot that once I'm screen sharing, it completely hides the top of my screen. So yes, it's pictured here. So in this one, these are in the plane, these hydrogens are sticking out, and these hydrogens are sticking in. So in a Newman projection, it's essentially looking at this molecule from a different perspective, because like from skeletal drawings and the 3D drawings, we've always just kind of been looking this perspective. We actually take a projected bond, in this case, this carbon-carbon bond, and we kind of rotate the molecule to the side. So this bond is hidden, and we just see these free hydrogens sticking out the sides. So when we do this, because these hydrogens are in the same plane, and these hydrogens are in the same plane, and these hydrogens are in the same plane, when you rotate it, they overlap and they're hidden from view. And so in Newman projection, we literally just draw what we've seen here. So this is what it's going to look like. So this is the molecule that we've just seen. And a lot of times when you see Newman projections, they kind of specify from which perspective you're seeing it. So in this case, so they'll draw like an eye to the side. So in this case, we're looking at this molecule, and this hydrogen with the blue bonds is going to be closer to us. And this carbon with the yellow bonds is going to be farther from us. And so based on what we've just seen, this is what it's going to look like. And this is what the Newman projection is going to be like. And I'm just going to break this down. So this purple in the center, I use that to note these carbons. And so we would only see this first carbon. This carbon in the back and this carbon-carbon bond, they're hidden from view because they're overlapping. And so we don't really see them. And so from the center, it sticks out these three blue lines. These are the bonds to this front carbon, the carbon that we see in the front. And then in the back, these yellow lines that are sticking out from the circle, these are the bonds to this back carbon. So the carbon in the back. And also, if this drawing was going to be like completely accurate, we wouldn't actually be able to see these yellow bonds because they would be overlapping. But because we actually do care about them, we kind of draw them off to the side a little bit. And here's like a more like official looking drawing if you want to see this. I just hand drew all of these because I know you guys are very curious about like how you would draw these on an exam. And so like notice how like they draw like their back hydrogens kind of like clockwise to the front hydrogens. In this case, I drew them counterclockwise. It doesn't really matter, just draw them either way. I don't think in 3570 they would take off points for like where you would draw them as long as like they're right next to each other and it's clear that you understand that they're overlapping. But this isn't the only way we could draw alkane. So if you remember from Gen Chem, single bonds can actually rotate. With double bonds and triple bonds, you have that p orbital kind of locking them in place. And if you were to rotate the molecule, you would have to actually break those bonds. But in this case, the sigma bond, it can freely rotate. So let's take these yellow hydrogens and just kind of like twist them over a little bit. Once again, I'm gonna have to do this. Okay, so it's gonna look something like this. So these hydrogen, this carbon from this perspective is the same. And this carbon, I've kind of just twisted it over. And so let's see what it's kind of hard to see exactly what's going on from this perspective. And that's the reason why we're gonna view it from the point of a Newman projection. So once again, our eye is on the left side, and we're gonna see what you would see from that perspective. So it's gonna look like this. Now notice how these hydrogens are no longer overlapping. Instead, they're kind of sticking out, they're kind of staggered. And so we would draw a Newman projecting looking like this. So you would have your front carbon, and then these three bonds sticking out, and then back carbon, and these three bonds are sticking out halfway between the bonds of the first carbon. And so your Newman projection will look a little more like this. And so yes, you can see the blue bonds sticking at the center, that's the closer carbon, the yellow bonds, that's the farther carbon. And I've just color coordinated these hydrogens, so it's kind of simple to see what I've done. So from before, these yellow hydrogens were overlapping. Now I've just been shifted over 60 degrees. And so, like, once again, these red hydrogens used to be overlapping, these blue hydrogens used to be overlapping, but I've just twisted the molecule. Here, once again, I'm slightly more official looking drawing. And so I just stole this page from the textbook. It basically goes over what I just said. So in Newman projection, you're basically looking along a projected bond. Usually if you have a big molecule, they'll specify which bond you're looking at. But you're looking at this bond, and so because carbon, it's always bonded, or almost always bonded to 4 things. So beyond this carbon-carbon bond, it's going to have 3 substituents sticking out, and this carbon in the back is going to have 3 substituents sticking out, and you just draw these substituents. And then this Newman projection makes it easier to see the spatial orientation. So you can see if these substituents, are they going to be overlapping, or they're going to be kind of staggered. One term you guys should keep note of is dihedral angle. That's going to be the angle between the substituent in the front and one of these substituents in the back. It's that angle between the two. So in the staggered conformation, it's going to be 60 degrees. You know that because around a circle, that's 360 degrees. And then 1, 2, 3, 4, 5, 6, there's 6 parts. 360 divided by 6, that's 60 degrees. Are there any questions up to this point? It's a bit hard for me to see chat. Okay, if not, I'll keep moving on. So you might have a question. Why does this matter? Like, why do we even care? Like, so from these Newman projections, we can very clearly see the differences between this conformation and this conformation. By the way, I'm using conformation to indicate the spatial, like a different spatial arrangement of a single molecule, but they're both Fa molecules, right? They're both 2 carbons, 6 hydrogens. What's the difference between this form where the hydrogens are overlapping and this form where the hydrogens are kind of staggered? We also call this form where it's overlapping, we call that the eclipse conformation. And once again, this is the staggered conformation. So what is even the difference between the two? And the thing is that they actually have a difference in energy levels. In organic chemistry, one big concept is it's not just the elements and the bonds that make it a molecule that give it its properties and its reactivity. The spatial orientation of a molecule actually plays a very key role. And that's a concept we're going to return to over and over again in organic chemistry. So looking at these 2 molecules, they have a difference in energy. Do you guys think you can guess which one has higher energy? And also remember, higher energy means less stable. Does anyone have any ideas? Feel free to be wrong. You can be wrong. Staggered. So you think staggered has higher energy? Yes, second one has higher energy. That's a very good guess. Here's a hint. One thing you need to keep in mind with atoms that aren't bonded is repulsion. So elements, remember, they're surrounded by this electron cloud, and electrons, those are negatively charged. So electrons, are they going to be attracted or repulsed from other electron clouds?
Wait, I'm sorry. Can you clarify which one's the eclipsed and which one's the staggered again?
Okay, yes. So this first one, that's going to be eclipsed. And you can think of that as like an eclipse. In an eclipse, the sun blocks the moon blocks the sun. That's what it means. They're kind of overlapping. And staggered is going to be the second one. So they're kind of spaced out like this. Good question.
So if electron clouds repulse each other, does that mean that the eclipsed has higher energy?
Exactly, you're exactly right. Because in the eclipse conformation, these hydrogens are closer together, and the staggered, we managed to space them apart more. So this staggered energy level, that's going to be your lower energy, and this eclipse is going to be your higher energy. And so we can draw this out in an energy diagram to show what that means. So this is our energy diagram. So this x-axis, that's going to be your dihedral angle. So it's going to be the angle between these hydrogens in red. So starting from here, angle of 0 degrees. From 6 degrees, it's kind of staggered. Alexandra, you have a question?
Oh yeah, I'm sorry. I didn't mean to interrupt.
Oh no, it's fine.
So why would the ellipse happen? That's just happening when the electrons are naturally moving. Like normally it would be just the open spacing.
That's a very good question. It's something I'm going to touch on later on. But yeah, really, really good insight. I'll like start talking to it more once I've explained the differences between these two. So yeah, from 60 degrees between the two, it's kind of staggered. Once it's 120 degrees, this wet hydrogen, so it's overlapping with the next substituent, so it's back to being an eclipse. Eclipse, staggered, and at 360 degrees, it returns back to what it was at 0 degrees. You've just cycled back to the beginning. And so like as we said before, as you can see here, your eclipse conformation, that's highest energy, staggered energy, staggered conformation is going to be your lowest energy. Also keep in mind this y-axis, that's going to be your energy level, but it's just relative energy, like it's not actually labeled. So this staggered conformation, it looks like it's going to have an energy of 0. That's not accurate. It's just like relative to this eclipse, it has lower energy. If you draw this line starting at like the x-axis or even like a little higher, those wouldn't be wrong because this is just relative energy. And then going into what Alexandra was saying, so this energy diagram is actually something that we've seen something similar to it before in general chemistry, and that's going to be the energy of a reaction. So I'm going to use this as a metaphor for what I'm going to talk about next. So when you have this energy diagram, you start off with the energy of your reactants, and you go to the energy of your products. And so the big thing stopping your reaction from going here to here is this high energy transition state. You have to get over this high energy state in order to get to your products. So it's very similar to what's happening here. So let's say, like I said before, this molecule, it can freely rotate. So let's say you have this molecule in this 60-degree dihedral angle, and you want to rotate this hydrogen to be over here at 180 degrees. The thing that's preventing this molecule from going is this high energy eclipse conformation. It has to get over this energy hub in order to rotate here. So yeah, it is kind of similar to the whole concept of like activation energy. If your activation energy is very low, the reaction would happen a lot. If the activation energy is very high, this reaction wouldn't happen very frequently. So looking at this energy level, it's going to be 3.0 kilocalories per mole. I know the numbers don't really mean much to you at this point, but just know this is actually a pretty low number. So basically at room temperature, there's enough kinetic energy in the air from like collisions that this molecule can get enough energy to get to this eclipse state and then rotate back and then go back here. Also keep in mind, molecules usually like to be stable. They like to be at the lowest energy level possible. So if you see situations like this where it can be in high energies, then the probability of this molecule being in this high energy state. So essentially your ethane molecule will just be rotating freely. It's just that if you can't, with alkanes, you can't actually usually isolate the molecule in a certain conformation just because this rotation happens so quickly. At room temperature, it happens at a really, really quick pace. But like if somehow you would just like take a bunch of alkanes and somehow like freeze them or something, I wouldn't know how you would do that. And trying to total how many it was in each state, there would be a high proportion in staggered than there would be in eclipse. But like that's usually not something we think about because this rotation happens so quickly. We essentially just think of the alkane as being in all of these states. Does that answer your question, Alexandra?
Sorry, yeah, it does.
Okay. So let's look at something that's a little more complicated. Let's look at butane. So once again, this is going to be an alkane. It has 4 carbons. And yeah, really familiar yourself with those prefixes because it's going to come up over and over again in organic chemistry. So we're going to look at the energy diagram for this molecule. This one's going to be slightly more complicated because it's not just hydrogens that are going to be your substituents. In this way, if we're looking along this bond right here in blue, we would have on each carbon, there's going to be 1 methyl group and then 2 hydrogens. And remember, it's methyl because it's 1 carbon. And so it's a little similar to what we've seen before. So in this case, clearly all the eclipse states, the ones where the substituents are overlapping, those are high energy states. And the staggered states where they're kind of spread out a little more, those are going to be your low energy states. But the thing is that not all our eclipse states are equal and not all our staggered states are equal. And so I'm going to bring up some new terms. So looking at the substituents, you have your methyls and your hydrogens. And so remember, the energy states are caused by differences in repulsion. So what do you think is going to be repulsed more, these methyl groups or these hydrogen groups? And one hint is that think of the size of these substituents. So these methyl groups are going to be so much bigger than these hydrogens. So is it going to have more repulsion or less repulsion?
More.
Exactly, these bigger groups are going to have more repulsion. So as you can see from here, our lowest energy state is where you get these bigger groups, these methyl groups, as far apart as possible, 180 degrees apart. And our highest energy states are where these methyl groups are as close as possible, when they're 0 degrees apart. And so if you walked through this whole energy diagram, that would make sense. So in this case, when it's a dihedral angle of 0 degrees, they're completely overlapping, that's going to be our highest state. And then we just move this methyl group over slightly. And this is going to be what we call a gauche state. That's going to be when our biggest groups are like right next to each other, but still staggered. So this is going to be a very low state, but it's still going to be a little bit of repulsion. And then we can move this methyl group over 60 degrees again to 120 degrees. And now each methyl group is overlapping with a hydrogen. So it's going to be an eclipse state, and it's going to be a lot of repulsion, but not quite as much repulsion as there was over here at 0 degrees. And then we just move this methyl group over one more time, and that's going to be our lowest energy state. So we've spread out these methyl groups as far as they can possibly be. And then we move it over 60 degrees. And then once again, it's eclipsed, and it's overlapping. It's going to be the same energy as this, even though this one's pointing to the right and this one's pointing to the left, because it has the same overlap, the same repulsion. And then we move over 60 more degrees. It's going to be back to a gauche state. And then we move it 60 degrees and just return to original state. In this molecule, just because we have the same substituents on each side, it's a very symmetrical looking diagram. It's not always going to be the case. Sometimes you might have more complicated molecules, but you should still be able to solve this energy diagram, just keeping into account which ones are going to be your biggest substituents, which ones are going to have the most repulsion, which ones are going to have the least repulsion. And that's how you'll be able to create energy diagrams. And also just talking about the energy differences. So in this case, it's also not very big energy differences. So butane can also freely rotate at room temperature. I think basically all alkanes can freely rotate at room temperature. So we always think of alkanes, they're like freely rotating around these single bonds. Oh yeah, Sharon, do you have a question?
Yeah, you mentioned something being in like a gauche state. Can you explain what that means?
Oh yeah, very good question. I'm actually going to review the terms right now because I went over that very, very quickly.
Cool.
That's a really good question. Okay, so yeah, I put these here. So let's go over it one more time because yeah, I went over it very quickly. So eclipse conformations, that's going to be where our substituents on adjacent atoms are at closest proximity. That's a lot of things just to say that they're overlapping when they're going to be in our states. So I wrote down some angles here, 0, 120, 240, and just you can see these in the energy diagram. So in this case, they're 0 degrees apart. And then if you rotated it 120 degrees, it would essentially be overlapping with the next substituent. You rotate it at another 120 degrees, so that's going to be 240, and that's going to be overlapping with the next substituent. So that's what I meant by these angles here. And remember this theta, that's going to stand for dihedral angle. And so one subset of an eclipse is going to be the total eclipse conformation. On this picture, it's called the syn-periplanar, just because it means that they're on the same plane. I don't believe that this term is ever seen in 3570. It is something you might see if you're looking at this like online, so just keep that in mind. But usually in class, we can just call this total eclipsed, or you might even just get by just calling it eclipse conformation as long as you clearly indicate that this state is going to be higher energy than this state. So total eclipse is going to be higher energy than just regular eclipse state. And then staggered conformation. So staggered is going to be where we kind of spread out our substituents so they're farther apart. So it's going to be our low energy states right here, and it happens at 60 degrees because they're 60 degrees apart, and then you rotate it another 120 degrees, and then it's going to be halfway between these two substituents. So it's still going to be staggered, and then you rotate it at another 120 degrees to be 300 degrees, and that's going to be between these two substituents. And then gauche is going to be a subset of staggered conformations, and that's where you identify your two biggest groups, one group from this carbon and one group from this carbon. And that's going to be the conformations where they're right next to each other, just 60 degrees apart. So they're close to each other, but they're still staggered. So there's going to be some repulsion, but not as much repulsion as there could be. And so it happens here at 60 degrees, and it happens again at 300 degrees, because remember, this is a circle. If you rotate it 300 degrees, it's going to be 60 degrees from the other side. So just keep that in mind. And then another subset of your staggered conformations is your anti-conformation. In this case, it's called anti-peri. or 180 degrees apart, as far as they can possibly be. And that's your lowest energy states. And just as a quick review, which one's going to be your highest energy state? Is it going to be eclipsed, totally eclipsed, gauche, or anti?
Total eclipsed.
Exactly, totally eclipsed. That's going to be your highest energy. And which one's your lowest energy?
Anti.
Exactly, anti. And then gauche and regular eclipse. Which one's going to be higher energy, eclipsed or gauche?
Eclipse.
Exactly. So your eclipse states are always going to be higher energy, and just with the total eclipse being the very highest, your staggered energy states are always going to be your lower states, with the anti-periplanar state lower than the gauche state. Yeah, and I also took this picture again from the textbook, which goes over concepts again. It looks like we're pretty good on time. Does anyone have any questions about Newman projections? Okay, someone asked which page in the textbook. Give me a second. I actually have the PDF pulled up on my laptop. Let's see. Okay, this picture, the first. I'm just going to share my screen, honestly. Oh, the link for the textbook, I believe, is on the Canvas page. Yeah, we put it up there for your reference. So yeah, chapter 2 goes over alkanes, and it starts talking about different conformations. Let me just try to find the first page. And yeah, it goes much more into detail than I did. So yeah, this is the picture I took earlier. That's going to be page 49. Yes. So you can look at this. Also, we did publish a reading list on Canvas that will also have pages in the textbook that are relevant to our lectures.
Yeah, just to add, the textbook is on this discussion section on Canvas. So if you go to the discussion section, there's one that says like book link or something like that. You should click on it. It'll take you to a Google Drive where you can download the textbook. If you have issues with that, email us. We'll send it to you.
Yeah, feel free to email us if you still can't find it. Are there any other questions? So it's just hard to view. Okay.
Yeah, I just have a question. So are these slides posted under like week 1 resources? Or they're just posted?
Yes, they will be posted in modules under week 1.
Oh, okay, thank you.
So yeah, Sam and Sydney's slides should be up there already, and our slides will be there too. We'll try to upload slides before lectures if we can, because we know some of you are taking notes on your tablets. If we can't, we'll still upload them after lectures. Okay, it looks like we have a little bit more time, so I'm just going to do a quick practice to see if you guys just to get you guys familiar with this concept of a Newman projection. So I've drawn this Newman projection, and as I noted before, they're not always going to be symmetrical. So the thing in the carbon in the front is not always going to have the same bonds as the carbon in the back. So I know you guys, we have annotations enabled. So like if you see you were viewing Jennifer's screen share or whatever in green, and next to it there's like a little black button. If you hover over that, you'll see a drop down box. I'm just gonna mess around with this because everyone hates teaching on Zoom, but I just want to see if I can take advantage of some of the other options we have here. Does anyone want to try to, or even like multiple people want to try drawing a skeletal drawing of the molecule here, just so you can understand like the projected bond that's being hidden, and then the substituents that are sticking out. If you want, you can also try drawing a 3D drawing, but like also just a skeletal drawing would be fine if anyone wants to try doing that. Oh, it looks like someone's saying the lecture slide 1 slides aren't on Canvas anymore. We'll look into that. They might be unpublished because we were editing the Canvas page a while ago. Yeah, we'll look into that. They should be up by tonight. Okay, does anyone want to try just drawing this? Yeah, if not, that's fine. This is really intimidating. Okay. Wait. Okay, I'm just going to show it to you guys, and so we can just break down what's going on, because we are kind of running low on time. All right, so I've color coordinated this again, and yeah, just for ease of visualization. So this blue, that's going to be a carbon-carbon bond that's hidden from view. It's not specified that it's carbon-carbon, but like you could basically always assume that it's going to be a carbon-carbon bond, just because we're always using this to look at organic molecules. Those are always going to have like usually a carbon-carbon backbone. And usually we're looking at this to look at alkanes, I believe. So yeah, it will almost always be a carbon-carbon bond. If for some reason it wasn't, and that basically never happens, they would specify in like the prompt or something. But if not, just assume it's carbon. So you have this carbon-carbon bond. It's hidden from view in this projection. And then from here, we see these free substituents that are sticking out from the first carbon. So we draw them here. There's one methyl group, two methyl groups, and then this ethyl group. Yeah, that's ethyl, 2 carbons. And then from the back carbon, we have free substituents. So 1 hydrogen, 1 chlorine, it's going to be a chloral group, and then 1 methyl group. So hydrogen, chlorine, and CH3. And if we were to draw the 3D structure, this carbon, this methyl group here, and this methyl group here, we would draw those in the plane of the board, just sticking out at an angle. And then because we're viewing this from here, and then we would just like, from this perspective, this methyl group would be going into the page, and this ethyl group would be sticking out of the page. This hydrogen would be going into the page, and this chlorine would be sticking out of the page, because we're viewing it from here, from this perspective, we're viewing it off to this side. So in this case, this chlorine's closer, this hydrogen's farther, this ethyl group is closer, this hydrogen is farther. It's actually, go ahead, Noah.
It looks like on the left on the Newman projection, you have CH3 and CH3 on the like the closer carbons, but then on the right you have CH2 and CH3.
That's my mistake. Yeah, I think
Okay.
the rest of that 3 got cut off, but that's completely correct. That would be, a methyl group should always be CH3. But yeah, right now, the way I've drawn it, this carbon would have 3 bonds, which is incorrect. So yeah, very good catch. I'll edit the slides before we uploaded it. But yeah, good catch. It looks like it would just cut off. I was about to say something. Okay, so yeah, looking at things in the 3D perspective is a really important concept in organic chemistry, and it's really hard to do. So that's why usually they like, when you go into organic chemistry, they ask you to buy a 3D model kit. And so you can build the molecules and then be able to rotate them to look at them. And you're allowed to bring these kits into the exam with you. So if you're looking at this Newman projection, it's like, oh, it's so hard to like look at like a molecule and then look at it from the side. You will have that resource available. You will have model kits, and you can just build the molecule and look at it from the side. It's a good idea if you go on to like organic, if you want to like pursue organic chemistry, to be able to like do this in your head, but that's not a skill you have. You will have that resource available to you. And also like online, there are all these other resources. Like I have included the links to this page in my lecture slides. And so you'll be able, if you want, you can like look at these, and you can also like just Google. There's a lot of different resources online that will have 3D visuals of molecules, and you'll be able to Google them and look at them and like manipulate them.
Yeah, also I think Sydney posted some suggestions for what's it called, molecule kits. I forgot the name.
Yeah, there were sites where you could there were sites where you could like build a molecule. And
there's some
view
sites, websites, but also like to buy. So just check out the discussion section. There should be some stuff there.
Yeah, and also on YouTube, there's always people who are like building the molecules and then like manipulating it and showing it to you. So if you want to get familiar with how you would use a model kit, those are also very good videos. I believe, especially when we do cyclohexanes, we'll also pull up a bunch of videos that are showing how you would do that. Okay, I think that's everything I have for this lecture, and also time is up. If you guys have any questions, I'll be staying behind. I believe Ashley will also be staying behind, but for everyone else, feel free to leave. Thank you so much for showing up today.
Thank you.